Well, welcome everyone to today's webinar, Teaching Multivariable Thinking in Intro Statistics. I'm certainly looking forward to this one myself, aside from Ross Matusalem, one of our academic ambassadors, being a great presenter. I like that a lot of instructors are realizing that even in intro courses, we need to get students to start thinking of data in analyses in a multivariable sense. So I'm really looking forward to the topics that Ross is going to cover today. Now, there's a poll up on your screen just asking you what software you've used beyond JMP. We always like to see what our audience is using. Now there's a Q&A window and also a chat window. If you have a question, please put it in the Q&A window, not the chat window. It's going to be much easier for Ross and myself to answer the questions and make sure we're getting them all addressed and see which ones that we have answered and haven't answered yet. Now, if you want to make a general comment for not only us, but for the audience to see, that's not necessarily a question, you're certainly welcome to put something into the chat window, but try to keep the questions to the Q&A window. And I think, Ross, was there a calendar I saw for the upcoming webinars on one of the slides?
Oh, it was scrolling earlier, but that's all
Oh,
we
yeah,
have.
okay.
Today, you can always go to jump.com/academic webinars to view the upcoming webinars as well.
Yes, we have some more webinars in our spring webinar series. Now, in about a day or two, we will have this webinar posted on our webinar library, but you'll each receive an email from us with that link. So with that, Ross, are you ready to go?
Absolutely. Thanks, Kevin. And thanks, everybody, for joining to talk about multivariable thinking in introductory statistics courses. So teaching students to reason about relationships between more than two variables, even right when they're starting to learn statistics and learn statistical thinking skills at the outset. So I think we all understand in intro statistics, the focus is often on getting students to be able to perform basic univariate and bivariate analyses. The end point of a course might be somewhere around simple regression and one-way ANOVA, but we all know that the real world is more complex than those analyses can handle. I mean, and we want students to become aware of the importance of additional variables not involved in the analysis. And I mean, formally, we might talk about things like omitted variable bias, confounding, multi-factor interactions. And our students in intro stats probably don't need to know those terms and know what they are necessarily, but to just be aware of the fact that reality is often more complex than a simple relationship between an X and a Y variable. And so just to show you one example, so here, this is a data set we're going to start out with. If you've been to our webinars or ever seen me present, I like the penguins data set that we have here, where we have data on 344 penguins observed in the Palmer Archipelago of Antarctica. And so just to give you an idea of what I mean by multivariable thinking, let's take this graph, and I'm going to talk about how to make graphs and other things as we go along. So if you're new to JMP, don't worry, just sit back. I'm just trying to make a conceptual point right here. But here I have a graph of our penguins' characteristics of their bills or their beaks. So on the y-axis, we have their bill length in millimeters, and on the x-axis, we have their bill depth in millimeters. And we can see a negative relationship between the two. So when bill depth increases, and I should say bill depth is actually, you can think of it as like the height or the thickness or the width kind of, as that increases, bill length decreases. And that, I mean, strikes me certainly as a counterintuitive result. I would think that as one dimension of a penguin's bill gets bigger, the other dimension should get bigger as well. But in intro statistics, getting to simple regression might be the end of the course. And so then a student leaves that course and sees a graph or an analysis like this and says, okay, well, I guess that's the relationship between these two variables. But actually, what's happening here is that if we bring in, let's say, the species of the penguin, and now we have one regression for Adelie, one for Chinstrap, and one for Gen 2 penguins, we can see that the true relationship is actually positive, that within any given species, as one goes up, the other goes up. It's just when we lump them all together, do we get this erroneous result. And we want students to just be aware that when they're seeing something like this, the true reality might look something more like this, and they should question those bivariate relationships and bring those third variables into play. And we can teach that conceptually, this multivariable thinking, without getting into, say, multivariable statistics, or I should say multivariate statistics. Now, I want to point you to where I've relied, and I think many others, in shaping my own thinking about this. And this is a report from the American Statistical Association, or the ASA. And it's a report called the Guidelines for Assessment and Instruction in Statistics Education, otherwise known as the GAISE reports, released in 2016 and produced by a committee of thought leaders in the statistics education world. And they make a lot of great recommendations in that report, one of which is to teach multivariable thinking in intro statistics. Some of the others, include teaching statistical thinking and problem solving more than necessarily the mathematics behind it, using real data with a context and a purpose, and using technology, for example, like software. So I really recommend reading the entire report. You're going to get a link to the recording of this webinar and also this JMP journal file on the left that I'm using, and you can use this link right here to access the full report. But in that report, they stress that we should prepare our students for challenging questions that require investigating and exploring relationships among more than two variables. And that's emphasis that I've added there with the italics. But again, that's what we're talking about today. And so what I want to do now is show you in JMP some multivariable thinking examples or exercises using sample data that's built right into JMP so that your data are ready to go. And all of which that you can use in an intro statistics course. So just using basic graphs and basic analyses. So what we're going to do is first a brief introduction to the JMP tools that we're going to use in all of these exercises, and then we'll walk through each one. So Simpson's paradox, spurious correlation, and two-factor interactions. And along the way, I hope to show you that JMP really is a strong tool for teaching multivariable thinking or statistical thinking in general. Because if our goal is to teach students to think statistically, that is to question relationships between variables and explore additional possible relationships, what we want is a software tool that enables asking and answering questions easily on the fly. And JMP's interface really is great for that. I mean, I should mention I taught psych stat for a little bit using JMP for that exact reason. Okay, so we're going to stick with our Penguins data right now, and I'm going to introduce you to the JMP tools that we're going to use throughout the rest of the webinar. Now, this will probably be a review for our more seasoned users, but we always have some people who are brand new to JMP here. So let's just start with the basics. And so we're actually going to start with that graph that I already showed you, and we're going to create it in a tool called Graph Builder. So it lives at the top of JMP's graphing menu. I should mention while I'm here, I'm currently using the JMP Student Edition version 18. If you were here before the webinar started and you saw the slides scrolling, hopefully you saw that the JMP Student Edition is completely free software for academic teaching, learning, and research. So if you are looking for statistics software and you are a university faculty, just go to jmp.com/student to get your hands on the software that I'm using and know that your students can do the exact same thing. And again, it's totally free. So back to what we're doing here. I'm going to go into JMP's general purpose graphing platform, Graph Builder. And if you've never seen it before, it's a drag and drop graphing interface. So you take a column or variable from this list on the left, you drag it into one or more of the blue drop zones to build out your graph. And so I just dragged bill length to the y-axis. I'm going to take bill depth and put it on the x-axis. And JMP automatically creates a scatter plot in this case with what we call our smoother. This is actually a spline model. It's just meant to give us an idea of the trend in the data without assuming, say, a linear relationship. Now, why did JMP do that? Well, again, if you're new to JMP, know that JMP columns in the data table have associated with them some additional information, some metadata, one piece of which is its modeling type. So by that, I mean, is this a continuous, an ordinal, or a nominal variable? And you can see those denoted by the icons right here. So blue is for continuous, the red bars are for nominal, and you can just right-click there or on the same icons in the data table to change them. So that's what JMP used to know that, oh, continuous by continuous, I should give you a scatter plot. Now, I'm going to turn off the smoother using this ribbon of icons at the top and turn on the line of best fit just to get to that regression that we started with. So we're going to make a lot of use of Graph Builder today. And again, all you do is you drag your variables into the drop zones, and then up here you choose one or more of these graph elements to build out your graph. Now, one great thing about JMP for data exploration, for quickly asking and answering questions, is the interactivity of its graphics. So here, let me move this down just to demonstrate. And I want you to pay attention while I'm doing this to the bar graph back in the data table of this penguin species here. So if I'm teaching multivariable thinking, and at first I just put up a graph like this, I might say, well, first, students, note this is a pretty counterintuitive finding, right? We would expect this relationship to be positive. One other thing we might notice is that, well, it looks like we kind of have these clouds of points. There's one over here, another one over here, and maybe another one over here. So that's just interesting. And certainly in intro stats, one of the first things that students knowing almost nothing about statistics can do is just rely on visual pattern recognition when looking at a graph. And in JMP, what you can do is if you see something interesting, just click on it and see what you learn. So what I'm going to do in this case is pull up the lasso tool in JMP. You'll notice that my pointer is now a little lasso icon. You can also find these under the tools menu. And these are just different ways of interacting with JMP. The lasso tool allows me to draw a free-form selection area. So I'm just going to select this cloud of points. And again, I said pay attention up here. You'll notice with the highlighting of this bar, I've selected exclusively Gen 2 penguins. So what happens then if I grab some from this part of the graph? Well, that's just the Adelie penguins. And so, okay, we haven't seen any chinstrap penguins yet. What about these over here? Well, these are just the chinstrap penguins. So just using JMP's interactivity and being able to look across graphs when we make selections, you can start to learn some things about your data. In this case, I learned that species matters here. That's what these groups of points are. So let's bring species into the graph. And I did this briefly at the outset. But because we're focusing really on taking a bivariate relationship and bringing a third variable in, that's what we're doing today. I want to stress certain drop zones in Graph Builder that are good for that. So let's take species and first put it into the group X role. So what that does is give us a separate graph for each level of that third variable, broken out along the x-axis. We can see again, the relationship is positive. Group Y does the same thing, but breaks out the graphs along the y-axis. The wrap role in the top corner will create what's known as a trellis plot. So this is a grid of separate graphs. And then finally, what we did was an overlay. An overlay creates a separate graph for each level, but inside the same graphing frame or area. And that's the one that I think is particularly useful here. All right, so we could just use basically these graphs just to start talking about multivariable thinking and relationships between three variables. We used interactivity in order to identify that species was the correct variable for us, but that might not always be the case. In fact, the next example that we do, it's not going to be as easy as just clicking on a few points and figuring out what that third variable should be. So something that you can use when you want to just quickly assess many variables at once is a tool that's found all over JMP called the column switcher. So I'm going to go to the red triangle menu in the graph builder. All the way down at the bottom under redo, you're going to find the column switcher. And this is, again, all over JMP. Go to the red triangle, go down to redo, and you're going to find this tool. And what this is going to allow me to do is to select one variable that's already involved in my graph for analysis, in this case, species, and then select all the different variables that I want to be able to swap into that same role. In this case, I'll select all of them here. So I click OK. I also just dismissed those controls to give us a little more room. And now you'll notice if I click island, now island is our overlay variable here. And well, we still see a pretty steep negative relationship when it comes to the Bisco island here. So if I were a student just exploring these data, I'd say, I don't know, I'm still not seeing a sensible result with island. What about sex? No, sex is still showing me that weird result. What about flipper length? Now note that flipper length is continuous. So what JMP has done is split out the quantiles in this case in order to specify the groups or strata that we're going to graph here. And when JMP does that, you can always right click and specify the number of levels that you want to use. In this case, maybe I'll just use 2. And then I could do the same, let's say, for body mass. And so using the column switcher, I might be able to identify species here. You can see actually by switching to 2, though, it's collapsed 2 of those species together. Now, another thing I could do, let's just go ahead and bring our controls back. I'm going to remove our column switcher. We'll just go to start over and get our initial graph back. Let's say I'm looking at this, and instead of bringing that third variable in, what I want to do is be able to drill down into the individual species. Well, you can do that on the fly with the local data filter. So everywhere in JMP, you're going to find this tool under the red triangle menu right above redo, where we found the column switcher. So here I can say I want to filter based on species. Here, I'll actually click done again to get those controls out of the way, and update the graph to only be for the Adelie penguins, or only for the chinstrap penguins, or maybe even for a combination. So here's chinstrap and Gen 2. We've just excluded the Adelies, and we can see again, we get this positive relationship. In this particular example, one thing that's interesting is you can select the Adelie and Gen 2 penguins and find that those are really the drivers of this inverse relationship that we're seeing here. So this is a bit on Graph Builder, drag and drop graphing. Again, if I bring these controls back, we're looking for the group X, group Y, wrap, and overlay roles to bring in those third variables. You also have the column switcher and local data filter here. But now, if you're teaching intro stat, you might want students to actually start assessing the statistical analyses that you're teaching. So that is your t-test or your simple regression or your one-way ANOVA. And all of those can be found in a tool called fit y by x. So fit y by x, as the name implies, you just have one x variable, one y variable, and you want to analyze the relationship between them. This is, I mean, really an intro stat, a very foundational tool in JMP. So what I can do is put bill length in my y, bill depth in my x. So this is corresponding to the graph we made already. And JMP is going to give me the option to, let's say, assess the correlation or fit a least squares regression line. And I find those options under the red triangle. So I'm going to just go to fit line right here. And now I have that same graph that we started with, but I also have the full statistical report. So I can see the R square value, for example, or down here, I have the parameter estimate for bill depth along with its p-value. And all of the other tools we saw, the local data filter and the column switcher, are available here as well. So for example, I could go to the local data filter, filter on species and select just the Adelie or chinstrap or Gen 2, or even go back to that combination of Adelie and Gen 2 that clearly is driving this strange pattern that we're seeing. So we're going to use the Fit Y by X platform a fair bit as well. And the last one, just to give you one that I think plays a more specific role, but could be very useful and will be in one of the examples that we do. It's called the multivariate platform. Now, I said we're not really talking about multivariate methods today, so not things like, let's say, principal components analysis, but sometimes we may want to assess the pairwise relationships between a lot of variables at the same time, and this platform is quite good for it. So I could take all of our continuous variables, put them in the Y columns role, and when I click OK, I get a correlation matrix at the top and a scatter plot matrix down below. So I can numerically assess and visually assess the pairwise relationships between all 4 of these variables here. Now, what I like to do in the multivariate platform is turn this one scatter plot matrix into a really information-rich visual that you could use in a lot of different teaching contexts. One thing I like to do under the red triangle for the scatter plot matrix is turn on the shaded ellipses, which gives us a visual representation of the correlation. So the more elongated it is, the stronger the correlation, for example, right here. I also, under the matrix options, like to turn on the heat map so we can see deeper red values correspond to greater positive correlations, deeper blue to negative correlations. And I can also choose show correlations to overlay the correlation value in that heat map. And so this is a view that I really like when just assessing a lot of pairwise relationships. Know that if you have some view or some configuration of a report that you like, As of jump 18, it's really easy to save that as a template and reuse it. You're going to notice this star icon up at the top. So what you can do once you've configured your report is go to save a preset. And so what I've done is saved this particular configuration as a preset under my presets called heat map and pairwise. And so, well, actually, let me go back to what it looked like at the start. Once you've saved your configuration and then you launch the platform, it's as easy as just going to my presets and selecting it to get back there. So if you're using this with students, what I recommend across the board when teaching with JMP is to configure the main platform outputs the way that you like them or that you want your students to see them, save them as presets, and then in your JMP preferences, go to the platform presets section and use the export and import functionality. So you export your platform presets, put them up on your LMS, tell students to download them, and then go here and import them, and then they'll have all of your presets so that all of their platforms look the way you want them to look. All right. So that was an overview of all of the JMP tools you needed to know. And I did that because I presented all these up front instead of as we go, because now what I want to do is present 3 different exercises for teaching multivariable thinking, and in a way that we might do it in the classroom. So that is in a fluid question and answer, exploratory or investigative fashion without having to stop constantly between to introduce you to a new JMP tool and kind of break our flow. So these are all the tools that we need. Now let's move on to talk about these 3 examples. And you're going to notice all 3 examples really involve the same basic structure. And this is a structure that I kind of stole a little bit out of that GAISE report, where in one of the appendices, they have several examples of multivariable thinking exercises that involve presenting a bivariate relationship, an X and a Y, and then bringing in some third variable that maybe complicates the relationship, reverses the relationship, makes you question it, something like that. And so that's what we're going to do in each of these cases now. I'm going to leave the penguins data behind, though, of course, you could use that, that bill length and depth example if you wanted. And actually, that's an example of something called Simpson's paradox. If you don't know Simpson's paradox, this is the situation in which you find some relationship between X and Y, but then when you account for a third variable, that relationship reverses. Or I think also it might just go away, but canonically, or the most dramatic examples when the relationship completely reverses. So the penguins example is one of them. Here's another example using the diamonds data that's bundled in JMP. So I'm going to pull up the diamonds data. Now, I should mention, I don't think I showed this already. All of the data sets that we're using, you can find in the sample index under the help menu. So for example, here, I'm just going to go to diamonds. And if you click here, you can get a preview of the data set. And then you can click open to actually get to the data set. Now, I typically don't just use the data sets exactly as they come out of the sample index. I'll modify them a little bit for the purposes of, a demonstration or an exercise. In this case, you'll notice here we just have one variable, the color of the diamonds in the data set, using the standard color coding. And in the version that I'm using, I have the color code, but for students who might not be familiar with those, I have a description. So you're going to notice in all of the data sets I'm using, I've made some slight modifications like that, not to the data itself, but to the data table, like column names or something like that, just for the purposes of making them more amenable for classroom use. So you can always go to the sample index to get these data, but again, you're going to get a link after this where you can download my journal and you can click these buttons to get the version of the data that I'm actually using. And one other thing to say about this particular example is that actually this is not one that I came up with. Professor Dictevo at Williams College actually presented this example briefly in a larger presentation at a conference all the way back in, I believe, 2015. And this is also referenced in the GAISE report. So credit where credit is due. I didn't come up with this. But I do want to show you how it works because I think it's a good example to use with students. All right, so let's start out with a basic bivariate finding that we can get students to start questioning. So I'm going to use Graph Builder to just display a relationship between 2 of our variables here. I'm going to take that color description. So again, this is the color of the diamond. So let me just put it on the x-axis so we can see what we're dealing with. All the way on the left, we have faint yellow, 2 and 1. These are the least desirable colors. These are diamonds that have a little yellow to them. And faint yellow 2 has more yellow than faint yellow 1. All the way on the right, we have the most desirable, the completely colorless diamonds, where colorless 1 is really a total absence of color. So the desirability of diamonds moves in this direction. They get better and better as we go farther to the right. Now, let's bring in price. You would think then that the colorless diamonds should fetch a higher price. But if you put this on the y-axis, and let's say switch to a graph really appropriate for intro statistics, a bar chart. And actually, I'm going to use these properties on the left to add, let's say, a confidence interval on these bars. We get a counterintuitive finding here, much like the penguins one. The lowest priced diamonds are those with the best colors, the 3 colorless here. In fact, the diamonds fetching the highest price are these near colorless 3 diamonds that are getting, if you look in that hover label, $4,703 on average. And so this is counterintuitive. What is going on here? And in general, I personally feel like starting with a counterintuitive result is a great way to introduce multivariable thinking, because students will naturally want to question something that doesn't make any sense. If you show them a totally sensible relationship between 2 variables, they're probably totally fine just accepting it and moving on with their lives. So let's give them a bit of a conundrum and then see if we can get them to develop their multivariable thinking skills by solving that. Okay, so our initial finding here is that we have worse colors selling for higher prices. So let me just show you quickly then what the reality is before we move on to maybe how we would help our students discover this reality. And I'm going to show you how we get to this window at the very end. This is taken from our general purpose regression modeling tool, Fit Model, where you can build all kinds of linear models. And this is a multiple regression with just 2 main effects, color, but also the weight in carats of the diamond. And you can see something that makes a lot of sense here. So we have the relationship between price and carat weight here, and price and color description here. So obviously, as diamonds are larger weights, the price goes up pretty dramatically. But also, once we've controlled for carat weight, now we see a sensible relationship where the more colorless diamonds demand a higher price. But now let's talk about how we would help students discover this themselves, and it's using the tools that we've already seen. So what we might say is, well, hey, this is counterintuitive, but sometimes more than just one X variable matters. Let's bring another one in and see what we can learn. So I'm going to take clarity and put it into one of those drop zones that I stressed earlier. Let's just go with group X and see what we learn. All right, first off, I think now using bars, maybe this is a little too visually busy. So I'm going to change to a line graph, but we'll keep our confidence intervals. And so here I'm not seeing anything that at least makes the data look like they make more sense. Generally speaking, the colorless diamonds are still getting a lower price. We seem to get the higher prices around maybe the near colorless diamonds. So let's investigate more possible third variables. And if you're with me right now, then that hopefully makes you think of the column switcher. Let's use the column switcher, and instead of clarity, let's consider all of these variables. So let me get rid of our controls again. Now let's check out depth. Okay, so thankfully, even though depth is continuous, JMP has stratified this for us. And in each stratum, we see the same nonsensical result we saw before. Same thing happens when we look at table. Cut, yeah, I mean, it's not quite as messy, but we're still kind of seeing the same trend. But now, how about carat weight? Well, this looks dramatically different. We can see, of course, that the larger diamonds represented over here fetch the highest prices. It is their highest on the y-axis. But we can also see, crucially, that the relationship between color and price now makes sense. So for each stratum, that is each group of carat weights, we see a sensible positive relationship. So there we go. You can't talk about the relationship between color and price without also talking about carat weight. That's some multivariable thinking right there. Now, the last key here, I think, for students, and I'm trying to put myself back into an intro stat student mindset, is saying, okay, fine, I get this graph and I get that carat weight matters, but I have no clue why. I mean, this seems like magic to me that just suddenly worked. So we need to help our students understand why bringing carat weight in like this makes a difference. And so there's actually hints of that in this graph. What's really happening behind the scenes is that typically the colorless diamonds are cut into smaller pieces and sold at lower carat weights. And let's say the yellow diamonds, which not too many people are going to want to buy a yellow diamond, are sold in larger weights. And you can see some hints of that here. For example, if our students know that confidence interval width is determined in part by sample size, then we'd say, oh, well, the confidence intervals in the low carats are wider for bad colors versus good colors. And that reverses for the higher weights where we have wider confidence intervals here than here. So what might be happening is that we have very relatively few colorless high weight diamonds. And that turns out to be the case in these data. So what we want to help students then uncover is the fact that all three of these variables relate in a particular fashion that allows that counterintuitive finding to arise in the first place. So let's take a look at how we can do that again, just in Graph Builder, how we can help students develop that intuition. And here's another thing that I find some folks don't know about Graph Builder, but I think is really helpful when trying to assess more than two variables using it. I can do something like this. I'm going to put carat weight as the Y. And again, I'm trying to say that there's a crucial relationship between carat weight and price, but also carat weight and color. So I'll put price on the x-axis. Let me right-click here and actually change the marker size because there are a lot of points here. Now let's also take color description, and I'm going to put it in this drop zone, which is next to price on the x-axis to create two graphs. And I'm also just going to drag this smoother in so we get a smoother on both. And now we can see what's really going on. There's a positive relationship between weight and price. There's a negative relationship between weight and color description here. And in fact, we can even use that dynamic linking where I can select points in a graph to highlight, hey, when we're talking about the colorless diamonds, they're all around here. They're pretty low weight and low price. And so what's making those faint yellow diamonds sell for a high price is largely the fact that those are a lot bigger than the colorless diamonds. So there we have it. I mean, that's a full exercise. You could probably take a full class period starting with these raw data, presenting that counterintuitive finding, and then getting our way to this final understanding that we have. Now, where we ended up was that profiler, if you remember this right here. So let me show you a little something in Graph Builder that actually is quite handy. Let's say you've made a graph like this, and now you want to perform a regression analysis corresponding to it. Go to the red triangle, and you're going to find an option that says Launch Analysis. Now, what Launch Analysis does is take us into FitModel. That's that general purpose linear modeling platform. Whatever's on your y-axis will be our y variable. And your other variables, so your x-axis or your group x or your overlay, those will be main effects in your model. So right now we have price and main effects of color and weight. And I can click Run to actually launch that analysis. So this platform will produce a number of different outputs. For our purposes here, I mean, if we're talking intro statistics, students probably don't know much or anything about multiple regression until the very end of the course. So I might hide all this stuff and just go to factor profiling and select the profiler to show them, well, here, if we account for both x variables in the same analysis, leaving it vague exactly how we do that, then we get this sensible result. Now, actually, you can set platform presets again to simplify your outputs here. So when you go to that launch analysis and you get a full report, I've set up a preset It's just a profiler and summary so that it's nice and clean and easy for students. Now, I think we have time to do that or do this last thing that I want to mention here, because the next two examples are a little bit shorter. And that is demonstrate to you another way of dealing with third variables and stratification like we're doing here. So let's say let's see, just to simplify things, I'll remove the column switcher, bring up our control panel here. Actually, I don't think I need that. But so we're back at this counterintuitive finding that we started with. And what we're saying is, well, once you control for weight, the finding seems sensible. One way to do that is to bring weight into that group X and stratify, but you can also stratify using the local data filter. And if students can understand that stratified graph that we already built, hopefully this will further their understanding of what's really happening. So let's filter by weight. And what I'm going to do is actually look in just weight strata using the filter. In fact, I'll type it in. I'm going to look in windows that are, or stratum, that are quarter caret. And now you can see that if we're in the bottom part of the weight distribution, the relationship is sensible. And as we slowly slide along the caret weight distribution, always keeping the window a quarter caret in width, no matter where we put it, that effect looks sensible. And so if students can understand this particular demonstration along with this graph, which are two different representations of the same thing, I think they're really going a long way to understanding exactly how this third variable is coming into play. So to then recap, this is an example of Simpson's paradox, just one possible situation that you can use to teach multivariable thinking. You start out with the initial finding, that counterintuitive finding, bring in the caret weight as the third variable, and then our final understanding is that if you control for weight, then the relationship between price and color makes sense. All right, I'm looking up at the Q&A right now. It looks clean. So thanks, Kevin, for keeping up with that. And we will move along to our next example here, and that's one of spurious correlations. So by spurious correlation, I mean a situation in which our two variables, x and y, are correlated, but they're not causally linked, at least not directly. And really, we might need to bring a third or even more variables in to try to explain the initial correlation that we've observed. And just to flesh out this idea, I'm going to click on this link in my journal to take you to a website that some of you perhaps are familiar with, but others, this might be the first time you're seeing it. It's Spurious Correlations by Tyler Vegan. This has been around for about 10 years now, but what's happening here is that Tyler Vegan has assembled a data set of, I think, tens of thousands of variables and then mined them for all these possible correlations that just occur by chance, and then presents them in kind of funny fashion on this website. So for example, here we have today's correlation being the distance between Saturn and the sun correlates with Google searches for how to make a baby. And you can see a pretty tight correlation over time right there. Or down here, the second one, the number of movies that Amy Poehler has appeared in correlates with the total number of successful climbs of Mount Everest. Now, if you're not familiar with Amy Poehler, she's a famous comedian. Now, one thing that has been added recently, and I hadn't been to this website for a couple years, and when I came back when thinking about this topic, I noticed that they also have, for each correlation, an attempt by generative AI to explain it. So here we can see it says that as the number of Amy Poehler movies has increased, so have the levels of laughter and positivity of the world, leading to a rise in overall happiness, including mountaineers. And the joy and motivation that the mountaineers have received from these performances has caused them to try to ascend Mount Everest. And I mean, this is kind of absurd and funny, and that's the point. But also, this really gets at, I think, the idea behind multivariable thinking and spurious correlations. Generative AI has proposed intermediate variables here, unmeasured variables, right? So here we have the levels of laughter and positivity in the world. And then that led to a rise in overall happiness, which then caused for mountaineers motivation and so forth. So here we can see that we need to bring in more than just the two variables in order to explain this correlation. And that's what we're going to do in this example right now. So I'm going to use the US demographics data set. That's, again, like the others here, available in the sample index. In this data set, we have all 50 states in the US and various measures like their median household income, the mean IQ of the population, eighth grade math scores, the proportion of individuals who've attained a college degree, and also where we're going to start, the proportion of individuals who have reported consuming 5 servings of fruits and vegetables per day, which you can see ranges from 15.7% to 30.8%. And so as before, we're going to start with an initial finding that is a bivariate relationship, and that's that vegetable consumption is correlated with IQ. We started with Graph Builder before, but now let's imagine that we're maybe partway through our course. Students know what a correlation or a simple regression is. And so we're going to have them grapple with those statistics. In that case, we're going to be in fit y by x. So what I'm going to do is declare IQ as my x, vegetable consumption as my y. And then in our fit y by x window, I'm going to pull up the correlation. Now, if you're looking for correlation in fit y by x, you're not going to find this option that just says correlation. So really, there are multiple times when you might be interested in it. So you could pull up the summary statistics, and that'll give you the correlation. Or I personally prefer to go down to density ellipse, because that adds a density ellipse to the graph here while also giving me a report that includes the correlation. So here, the correlation is about 0.3, and it's statistically significant. Now, this might strike us as kind of absurd, right? Vegetable consumption is correlated with IQ, but I mean, you could try to come up with a probably inaccurate direct causal explanation. People of higher intelligence are more likely to make good health choices and consume more vegetables, or eating your vegetables makes you smart, right? And it would not be hard to elicit those kinds of explanations from your typical undergraduate statistics student. But odds are that's neither of those causal explanations are probably adequate or even accurate. And so the idea is to bring in third variables to try to explain why we're observing this correlation. So if you're thinking, oh, bringing in additional variables, and that makes you think of the local data filter, or excuse me, the column switcher, that's honestly where I would go next. So we're saying, well, vegetable consumption associates with or correlates with IQ. What else does it correlate with? And so I can use the column switcher and say, instead of IQ, I want to be able to swap out or between all of these variables. So let's take a look now. On the x-axis, we're going to have household income. And now our report, the correlation shows about 0.65, and it's highly statistically significant. Now, maybe we could create a plausible causal explanation here. Fruits and vegetables, fresh produce can be kind of expensive. And so folks with higher household income are able to afford and therefore eat more vegetables. What about eighth grade math? Well, that's positively correlated. Now tell me, does eating your vegetables make you get a better score on your eighth grade math exam? Or how could possibly getting a higher score on your eighth grade math exam cause more vegetable consumption? That's a lot less clear. Or how about this one, the proportion of smokers in that state? So this is starting to highlight how hard it is to really infer causality just because you saw a correlation. Does eating your vegetables make people quit smoking or less likely to start smoking? I'm really not so sure about that. So let's now highlight the fact that what we're really dealing with is typically many variables, especially in an observational situation like this, can be highly correlated with one another. So if you recall, we took a look at the multivariate platform at the outset here. So let's take all of these variables, put them in the Y columns role, and click OK. And I'm going to use my platform preset here to get back to our heat map. And I'm going to make this just a little bigger so that we can parse it more easily. Now, first, let's find that correlation that we started with, the 0.3 correlation between vegetable consumption and IQ. So what we would do here is find vegetable consumption. It's right here on the diagonal. And so let's just draw a line straight up until we hit the IQ row, which is right here. So I'll draw over. So that's how we read this. There is our 0.3. I could do the same for the scatter plots. So let's go over until we hit IQ, which is down here. And so here's the scatter plot representing that correlation. So we already said, well, yeah, vegetable consumption correlates with IQ. It correlates with a lot of different things. I mean, the two highest correlations actually are with household income, 0.65, and with the proportion of people with a college degree, 0.71. And so we already talked about how maybe you could imagine a causal link with household income. You could also imagine college degrees being some kind of intermediary that brings IQ into the mix. So that is, people with a higher IQ are more likely to achieve higher levels of education. So here are the correlations of IQ and high school graduation and college degrees. So if you have a greater degree of education, we know you're probably more likely to get a higher household income. And that's clearly the case according to these two correlations. And then once you have a higher household income, it looks like you're more likely to eat vegetables, perhaps because you can afford them. So now we're starting to come up with an explanation that involves a number of different variables. And we can start to come up with those explanations and test those theories just by checking the correlation values in this matrix and making sure that they generally make sense. The things that should be correlated are. But now let's talk a little bit more about what we would do next once we have this potential explanation. And I'm going to stick with household income as the third variable here. So let's go back to what we've been doing from the outset, and let's just make a graph now that tries to incorporate that third variable that we've identified. So I'm going to take IQ and put it on the X. I'm going to take vegetable consumption on the Y. I will pull up our density ellipse, and down here I can ask for the correlation. And now I can just take household income and put it in, let's say, the wrap role this time. And maybe I'll change the number of levels here to just 4 to come up with a nice square. And now we can see, while we still get a correlation of 0.3 in the lowest quartile of the household income, that reverses to negative 0.24 when we get to the next quartile. And then for the top two, they're both at about 0.08, so pretty darn near 0. So it looks like once we, in a very informal sense, control for household income, I'm not so sure that this correlation actually exists. So let's verify that. Let's go to launch analysis as we did before. I'll click run and then use my platform preset just to get back to the simplified view. And what we can see is that when we analyze vegetable consumption according to both IQ and household income matters a lot. IQ doesn't really matter at all. In fact, the effect is not statistically significant. If I click on household income and then remove to take it out, we can see that's when we find this spurious relationship that we started with. So that's our final finding in this case. We start out with a somewhat ridiculous correlation, and using our own knowledge in combination with the patterns of correlations among many variables create an explanation that seems to make a little more sense to us. And then we can confirm that graphically and statistically. So with just the few moments we have left, let's take a look at one last example. And this one is actually the shortest of all, so we'll have a few extra minutes to field what remaining questions there are in the Q&A. And this is an example of a two-factor interaction. I think if you're on this webinar, you're well aware of what a two-factor interaction is. We have the effect of X on Y depending on some other variable. And to keep things in a way that intro stat students would be able to comprehend, we're going to say that that third variable is a person's membership in a particular group. I'm going to use the diabetes data set that comes bundled in JMP. You'll notice that I've labeled it variables added because I've added a couple variables for the purpose of this demonstration, but I think it does make it a good data set for a generally accessible example of a two-factor interaction. We have data here on 442 diabetes patients, and we have a measure of disease progression over the course of a year, where higher values indicate greater disease progression. And then for each person, we have information like their age, their sex, their BMI. The two variables I've added that you won't find in the data table that's built into JMP is family history. So whether they report a family history of diabetes, and then also what their level of physical activity has been leading up to that disease progression measurement. Now, our initial finding here is that high physical activity is associated with lower progression. And we can find that using fit Y by X right here. So let's say that we were going to look at physical activity as our X, progression as our Y. So we're in fit Y by X, the one-way version, which allows us to perform an ANOVA. And here's our ANOVA result. It's statistically significant. And we can see with these means diamonds, where the central line indicates the mean, that we have an effect where the high group is showing lower progression than the other two. And so this is an example of a completely intuitive finding. You'd say, oh, okay, physical activity is actually aiding somebody's health. But I think whereas before we led with counterintuitive examples, it's really important to get students to a place where they know to question even intuitive relationships that they might find. And that can help them make or become responsible consumers of statistics, which, in an ideal world, everyone would be. So I might ask somebody, okay, based on what you're seeing here, what physical activity would you recommend to a patient? And of course, everyone's going to say, well, just high physical activity. And then we can throw a wrench into that by using the local data filter. So let's filter on family history. Now, if we look at only patients who reported a family history, we see the same pattern here. And so for those folks, yeah, I really think you should be exercising a lot. How about no family history? Well, in this case, the effect completely goes away. We don't even have a statistically significant effect at all. So the reality might be that the advice a physician should give a patient will depend on what their family history is. Advise high physical activity for people with a family history, but not for the other folks. This is just a canonical and I think relatively easy to grasp example of a two-factor interaction right here. And all you really need is fit Y by X and the local data filter to highlight this for students. Now, of course, what we'd probably want to do is create a graph that shows the full relationship. So let's put progression on the Y. Let's put physical activity on the X. I'll switch to a line graph with a confidence interval on the mean right there. And then we'll take family history, and you could put it into the group X role or the group Y role. In this case, I think it's a good time for an overlay. And now we have a canonical interaction plot right here that really makes the point for us that the pattern that we're seeing in the no group is very different than that we're seeing in the yes group. And then, of course, you might say, hey, students, what other interactions can you find in this data set? Or does your advice regarding physical activity depend on anything else about the patient beyond their family history? And so that's an easy thing to do in JMP. Let's just go down to our column switcher and say, instead of family history, let's be able to switch between any of these variables. And let's take a look at age. Now let's go ahead and get the number of levels down to something manageable like 2. Okay, age, those look pretty parallel. I'm not sure there's an interaction there. How about sex? Oh, sex might matter, right? And students can now easily start exploring these to try to figure out what other variables, what other third variables might matter and might change the advice that they would give. So in this example, though, there's a clear effect with family history. And in particular, again, only those reporting a family history show an effect of physical activity at all. So that's just a quick two-factor interaction one. This could actually be a good preface if you're starting to teach multiple regression or factorial ANOVA, a way to start highlighting not just multivariable thinking, but why the specific notion of an interaction is important. But to zoom back out here, what have we just done? So we've talked about multivariable thinking. We showed you some jump tools that you should know if you want to start teaching multivariable thinking to intro statistics students specifically. So we never really did multiple regression. We just showed some profilers. It was all graphs and basic simple regression and ANOVA. And really, those weren't even necessary. You could do everything in Graph Builder. And then 3 different examples, hopefully, that you can use, or at least give you an idea about how maybe you could take some existing examples you have for your course and modify them to start getting students to think about beyond just the X and Y relationships. So thanks, everybody, for your attention. In an extremely rare turn of events here, we're done about 5 minutes early. So, Kevin, do we have any questions that are good to address live?
Let's see, a couple just popped up and I'm in the middle of answering. One I'm answering, but maybe since we have a little time, you can show. So, when you are bringing in a third variable into the wrap role and then jump's going, and it's a numeric continuous variable, then jump's going to obviously pick the number of levels. Just showing how if you just right click on the variable name in the wrap position, you can like customize how many levels, and you can even choose like the cut points.
Yes, that's right. So once you've put something in the wrap role, or I mean, the same goes for the overlay role, you're going to see its name in the graph somewhere. Go ahead and click on it. Under levels, you can either change the number of levels here, which I did, admittedly pretty fast a couple times. So I have it set at 2. If I set it to 3, now you can see I have 3 different levels. Or, as Kevin just alluded to, you can actually use this tool to declare custom levels. So you can add or subtract the number of levels that you want, and you can specify their cut points, either by typing them in or interactively changing them right here. And once you click OK, it will obey those new cut points. I just did that on the fly, and so obviously I didn't do a very good job because this final plot makes no sense. But otherwise, that's how you would do it. Right-click, levels, and then either change the number of levels and let jump make them equal quantiles, or do something custom.